This lesson is about sequences. A sequence is a pattern that has a list of numbers called terms, and we will find the pattern in that list if we look at how we get from one term to the next. This pattern is pretty simple. It starts with 3 and then simply adds 2 to get to the next term and the next and the next. Sequence notation uses an a sub n. The n represents which number or which term in the sequence we're looking at. So if the first number was 3, we would call that a sub 1. The second number is 2, so we call that a sub 2. The third number or third term is 7, so we call that a sub 3, and a sub 4 for the fourth term, and so on. Sequences can also be shown or listed in tables. So if we say 1, 2, or 3 for the number or term, then a sub n would give what the actual value is. So the first term is 3, the second term is 5, the third term is 7, and so on. So the n represents which number, and the a sub n would represent which term. So if n equals 1, then a sub 1 is equal to that term, which is 3. If the second number is 5, when n equals 2, a sub 2 equals 5. So the n represents which term, and then a sub 3 would represent that that is the third term. So the third number in the sequence is 7. We can also give the pattern using an equation. A sub n equals 3 plus 2 times n minus 1. The way that this works is that when we want to find the first number, we would plug in 1 for n, and so on. So if we change every n in that equation into a 1, we can then solve that or simplify that to find out what the first term is. In this case, the first term was 3. If we wanted to find the second term, we could make the n be 2. If we wanted to find the third term, we could make the n be 3. So plug in the term number you're looking for the n in the equation. In your homework, you're going to be asked to find the first 3 terms of a sequence when you're given the equation. So if we have a sub n is equal to 3 to the power of, oops, that shouldn't be an x, that should be an n. Yay, let's fix it. Woohoo, there we go. A sub n is equal to 3 to the power of n plus 2. That means we're going to plug in 1, 2, and 3 for n so we can find the first, second, and third terms. We can make ourselves a table and then do our math. When we plug in 1 for n, we get 3 to the power of 1 plus 2, which equals 5. When we plug in 2 for n, we get 3 to the power of 2 plus 2, which equals 11. And when we plug in 3 for n, we get 3 to the power of 3 plus 2, which equals 29, which means that the first 3 terms of this sequence from the equation are 5, 11, and then 29. You can keep going if you wish to find any term of the sequence. The final example we're going to look at is when that sequence is given by a model or picture. Sometimes we'll have diagrams or pictures to represent a sequence or pattern. In this case, we're going to look at each diagram number and identify how many squares are in that picture to see what the value for that term of the sequence is. So the first diagram has 3, the second has 5 squares, and the third diagram has 7 squares, which means our sequence is going to be 3 and then 5 and then 7. We can continue that pattern to find the next diagram in this sequence. We know that the fourth term, if we add 2 each time continuing this pattern, would have 9 squares, but we also want to make sure those squares are in the correct location. If you look at the pattern, we start with 1 square down on the left, and then it adds those squares to the top and to the right as it continues to grow. So to show that fourth diagram, we would start with 1 square, and then add 4 squares to the right and 4 squares up to continue that pattern of 9 squares in the same pattern that it was shown in the first 3 diagrams.